So, good morning, students. So, today I will discuss Reynolds equation in two dimension. So, this derivation is very much important in case of hydrodynamic lubrication. And using these derivations, the hydrodynamic theory is explained in a better way. So, before going for the derivation, I'll just give you uh, a brief introduction about Reynolds investigation. Say Reynolds, who is a Professor D. Reynolds, name of the person who derived this equation, and the motive behind deriving the Reynolds equation is Tower's experiment. So Tower is also a name of the person engineer who kept on studying the behavior of the lubricant under various conditions, and he had postulated his own theory regarding the hydrodynamic lubrication using Tower's experiment. Anyhow, for your syllabus, Tower's experiment is not included. Earlier, before scheme, we had this Tower experiment. So for this scheme, it is excluded. So I will not discuss much on Tower experiment. But for deriving Reynolds equation, Tower experiment is considered to be the base. Okay, so Professor D. Reynolds was inspired to apply the laws of hydrodynamic to explain the results which are obtained through Tower's experiment. So, in his classical work presented in the year 1886, look at the year 1886, more than 100 years. It's been more than 100 years deriving this equation. Still, it holds good. Which has been starting point for many later investigation of lubrications. Reynolds made the following significant contribution. First contribution is he gave the general picture of the physics of fluid film lubrication. So with this equation, he gave the general picture, overall picture of the physics behind fluid film lubrication. So then he showed the importance of viscosity of a lubricant on the friction characteristics, load, capacity, and other characteristics of bearing performance. Next, he showed the importance of bearing clearance with this expression, and also he showed significantly that a lubricant on which it adheres to both the moving and stationary surfaces of bearing develops a positive fluid pressure in a converging portion of the film, and this pressure supports the load, preventing direct metal to metal contact between the bearing surfaces. He also showed that no such pressure can be developed between two parallel surfaces, and he derived a differential equation for the pressure distribution in the oil film. And this equation became a basic equation in the hydrodynamic theory of lubrication. So applying this equation, Reynolds was able to explain the results of Tower's experiment. So he got a link, he created a link between Towers experiment and this Reynolds two-dimensional equation with the expression. So that is the significance of Reynolds equation. So in the examination, they may ask about the theory. I mean, what is the motive behind deriving the Reynolds equation? You can explain all these things briefly. And coming to the assumptions, so before going for any derivation, so we have to assume something. For example, in case of deriving a modulus or value for modulus of elasticity using Hooke's law, we have derived that the material is isotropic, the material is homogeneous, the material is loaded up to elastic limit, like that. See, assumptions are very important for derivation. So again, for this Reynolds equation, we need some assumptions, and it is very important to quote these assumptions during examination. See, what we observe evaluators when we go for evaluation of your answer scripts, we observe that many of you directly they jump into the derivation before quoting any assumptions made for the derivation. So keep in mind that these assumptions are very important and carries some marks. Some marks is allocated for these assumptions. If you miss that, definitely you will lose marks. So a strong appeal from my side, whenever you go for derivation, don't forget to state the assumptions made for that. Clear? So see that first assumption. So there is no flow in the direction perpendicular to the motion. So there is no flow in the direction perpendicular to the motion, means there is no end leakage. See, there will be some leakage in the bearing. Okay, so for derivation purpose, we consider the bearing is not yielding any leakage. Second assumption, the viscosity of the lubricant is constant throughout the oil film. See, as we are all aware that the viscosity value varies with the temperature and the pressure. So for the derivation purpose, we assume that the viscosity is constant throughout the oil film. The third assumption is the motion of the fluid in the film is laminar. Okay, so even in derivation of Newton's law of viscosity also we have stated the same assumption. The motion of the fluid in the film is laminar. Then the inertia forces on the oil film are so small that their influence on the pressure development in the oil film may be neglected. Okay. See, why students are admitting almost 10 minutes late? See, I may give maximum of 5 minutes relaxation. Beyond that, if you keep on joining, it disturbs the class. So normally, if the class starts at 11:15, no, I will give relaxation up to 11:20. Beyond that, it becomes difficult for me to allow you people. And also, don't forget to mention your USN in the chat box. So this will be considered as official attendance. As soon as you enter into the classroom, type your USN in the chat box. Okay, so one more assumption. The inertia forces on the oil film are so small that their influence on the pressure development in the oil film may be neglected. Next one. So no slip occurs between lubrication and bearing surface. And the fluid is incompressible. The lubricant is a Newtonian fluid, which means that it obeys Newton's law of viscosity. And the clearance between the two bearing surfaces is small, so small that the change in the pressure across the clearance can be neglected. So these are also how many points? Eight assumptions are made for this Reynolds equation. 8 assumptions. At least you should mention 5 assumptions. If you can't remember all 8. See, for any derivation, first you have to develop a differential equation. So for that, I will consider a unit volume, okay, of fluid or lubricant, which is there in the bearing. So just look at the analogy over here. So dimension, you just mentioned that this is a unit cell having a dimension dx, dy, and dz in all three directions, and pressure on the left hand is acting, that is P, and the right hand the pressure drops, that is dP. Okay, so dy into dz, it means the force, pressure into area. Area in this case is dy into dz. Okay, length into breadth. This is a rectangle one, no? One side it is a rectangle. So then force is pressure into area. That is P into dy into dz. Similarly, the pressure, the fluid on the other side, it'll be having a pressure of this kind, this value. P plus dP by dx into dx into dy dz. Similarly, shear stress on the top and also on the bottom portion, top face and bottom face. Shear force, tau is shear stress. Stress into area gives you force, shear force. And the bottom portion, the shear force given by this. So this is a small unit considered, and it is magnified over here. Converging oil film, considering the converging oil film. See, we have seen that in the previous class, in the while understanding the formation of continuous oil film in a journal bearing, we have seen that two portions being created in the bearing, that is the converging portion and the diverging portion. So that creates some kind of pressure in it, and that pressure is sufficient to lift the journal, and journal in turn runs concentrically with the bearing. Okay, so this is the converging film you have considered for the derivation, and a small unit volume of unit cell is taken out from that, and this is analyzed for forces. Okay, this unit is analyzed for forces. So figure, force acting on the element of the lubricant in x direction. This is the x direction. Okay, so considering conversion oil film as shown in the figure, and the surface B is the fixed. So this is the surface B is fixed, while A is moving with velocity. The above one is surface moving with velocity, and the below one is fixed. Why converging means some kind of inclined surface being created. Okay, so this is convergent part and this is divergent part. Moving with constant velocity u in the x direction, and this surface is loaded with vertical load W. The coordinate system is shown in the figure 2. So this is the coordinate system shown in figure 2. And the surfaces A and B are assumed to be large in the z direction perpendicular to the motion, so that the flow in this direction can be neglected. So consider an element of a fluid between the surface shown in the figure 1. So I'll just keep this figure. Consider an element of fluid between the surfaces as shown in this figure 1, and the same element is enlarged and shown in figure 2. The positive direction of the velocity components, that is u and v of the element, are shown, and the forces acting on the element are also shown in the figure 2. So this is figure 2, this is figure 1. And for equilibrium resolving forces, we have, say you have to resolve the forces for equilibrium condition. So it means that the sum of all the forces acting at a point is equal to 0. That is, sigma of all the forces is equal to 0. So that is the equilibrium condition. So applying that equilibrium condition, we'll have this equation. That is force on left side, P into dy into dz, this force. P into dy into dz, plus we'll have shear force. So like that, this force is acting opposite to this. You can have minus sign for this. We'll see here. See, minus P into P plus dp over dx into dy dz. Again, the shear force on the other side, tau x plus d tau x over dy into dy is equal to 0. So just cancel the common terms over here. So you P gets multiplied with dy dz, and we have a positive value over here and negative value. Two terms gets cancelled with each other. Similarly, shear force value, we have positive value and a negative value. Both are cancelled with each other. So what is left? Minus dp over dx into dx dy dz minus d tau x over dy into dy dx dz is equal to 0. Okay. So, so we can have this relation ultimately. So that is the dp over dx is equal to minus d into tau x, d into tau x over dy. So as per Newton's law of viscous flow, so that is this derivation we have made it in the beginning itself, Newton's law of viscosity. So we know that tau is equal to neta du by dy. This is from the expression, and we'll have modification for this. We'll introduce a negative sign. So what this negative sign indicates is pressure gradient. So pressure is decreasing from one end to the other end. So that is a pressure gradient. So then using this relation and substituting tau value into this formula, so what we get is dp over dx is equal to minus d by dy into minus neta du by dy. So then dp by dx is equal to neta into d square. This gets multiplied d square u divided by dy. So or we can have this d square u by dy on one side and remaining things on the other side, so that this will be used for integration. So we have developed a differential equation with regard to the velocity in terms of pressure. So I will call it as equation 1. So integrating this equation 1 with respect to y. So what is this y? So y is the distance, that is other direction. So this vertical direction. Okay. So what we get is velocity term, differential term. So d square becomes du or upper integration by dy is equal to 1 over neta integral of 1 over neta dp by dx into dy. Anyhow, this neta viscosity is constant. So I'll keep that value out of integration. So then I will differentiate, integrate with respect to these terms. So then du by dy is equal to 1 over neta dp by dx into y plus c1 is the constant. So this is constant of integration. So again, going for double integration, because ultimately our aim is to reduce it to velocity. We need expression for velocity by Reynolds equation. So du by dy, again integration, we will get value velocity u is equal to, so upon second integration, we'll get this expression 1 over neta dp by dx integral of y into dy plus c1 into integral of dy. So call this expression as 2, where we have two constant of integration, and it is to be eliminated. Okay, it is to be determined, evaluated with respect to the boundary condition. So applying the boundary condition. So when v is equal to 0, u is equal to u, it means maximum velocity. When when y is equal to h, u is equal to 0, minimum velocity. It means that the particles which are associated with the moving surface, that is when y is equal to 0, will have maximum velocity. I mean with respect to the particles which are associated with the surface A, that is moving surface, will have maximum velocity. And when y is equal to h, the particles which associate with the fixed surface, I mean the bearing block, so that will have 0 velocity. Bearing block is fixed, journal is moving, no? So that is the meaning. So this constants C1 and C2 can be determined by applying the boundary conditions. So now we'll just apply this boundary condition to the equation 2. So what we get is C2 is equal to capital U, that is velocity, maximum velocity, and substituting back into this equation. Okay, we get expression for C1, because C2 is U and the C1 will get this expression. And again, substituting C1 and C2 into the equation 1. So this is the equation 1. This equation 2. This is probably 2. Okay. So what we get is, so you look for the simplification. It's purely a mathematics, applying the concepts of integration and differentiation. So we will get the expression for velocity. So u is equal to 1 over 2 neta dp by dx into y square minus yh plus u into h minus y over h. So I will call this as equation 5. So equation 5 gives the velocity distribution across any section of the oil film. And the first term of equation 5, so it has got two parts, first term and second term. See, this first term of equation 5 gives a parabolic velocity distribution. Y square means parabolic due to the pressure induced in the film, which has this term u1 is equal to 1 over 2 neta, where neta is viscosity, dp by dx into y square minus hy. And the second terms gives linear velocity distribution. See, this velocity expression has got two terms. First term is represents parabolic distribution, and the second term represents linear distribution. So y is equal to x, like that, linear. Parabolic means y square, cubic y cube, like that. So when you go for a three-dimensional equation, you will get one more added term for this. Okay, since we restrict our study to two-dimensional equation, so up to this level is sufficient. Clear? Then we can have a derivation for flow rate also, but velocity Reynolds equation at two-dimensional is sufficient. Okay, so three-dimension they'll rarely ask, because this derivation goes to 4 to 5 pages. In the examination, normally they'll restrict their question to up to velocity, derive Reynolds two-dimensional equation for velocity. Okay. So with this, the concepts of the Reynolds equation, two-dimensional equation is clear. So if you have any doubt for this, I'll spare 2 to 3 minutes for the discussion. If you have any doubt regarding Reynolds two-dimensional equation derivation, you can ask the question. It is open to you. Because from my next class, I'm going to solve the problems with respect to hydromic lubrication considering Sommerfeld number. Okay, I will discuss the significance of Sommerfeld number, effect of Sommerfeld number, and how to solve the problems using Sommerfeld number. So again, these problems would be repeating one for you, because we have solved problems using Sommerfeld number in the design of machine elements too also. Same problems gets repeated here. So I will take those problems in the next class. Okay. If you have any doubt related to Reynolds two-dimensional equation derivation, you can ask me. Otherwise, I will end the session now. I believe no doubt from your end. So I will end the session for today. So I will take up problems on Sommerfeld number in the next class. Okay. So make sure that you have entered your USN in the chat box. Okay. Thank you. Thank you, one and all.